We're going to start this lesson by talking about absolute value inequalities. Remember when we dealt with absolute value, we had two solutions. Here, we're also going to have two solutions, but we also have to keep in mind that rule about when we divide by a negative that we change the direction of the inequality symbol. So in this case, we have the absolute value of v is greater than 7. So to solve this, we start by putting v is greater than 7. And then remember, we have to deal with the negative 7. So here we're going to have v is less than negative 7. Notice the sign switched because we're taking the opposite or applying the negative. So our two solutions would be v is greater than 7 and v is less than negative 7. So on the number line, we have our two boundary points, negative 7 and 7. So the values that are greater than 7 go to the right. And remember, when it doesn't equal, we can use an open circle or parenthesis. For the second one, the values are less than negative 7, so it's negative 7 and the values to the left. And again, we would use parentheses because it's just less than. Our next example, the absolute value of v plus 15 is greater than or equal to 20. So as we did before, we want to isolate first. So we have the absolute value of v is greater than or equal to 20 minus 15, which is 5. So again, we set up our two inequalities. V is greater than or equal to 5, and v, remember, switch the direction, less than or equal to negative 5. So if we're going to put this on a number line, we have our boundaries at 5 and negative 5. The values that are greater than or equal to 5 are to the right. And remember, because it's or equal to, we use bracket instead of parenthesis. And the other one is v is less than or equal to negative 5, so less than is to the left. And again, because it includes negative 5, we use a bracket. If we were writing our answer in interval notation, we start with the point furthest left, which would be negative infinity, and it stops at negative 5. Remember, infinities get the parenthesis. In this case, negative 5 is included. Since we have two intervals, we use union. The other one begins at 5 and continues indefinitely to the right to infinity. So since 5 is included, we would use the bracket. The next example, we have the absolute value of y plus 5 is greater than or equal to 2. So since it's already isolated, we set up our problem. Y plus 5 is greater than or equal to 2. And y plus 5, remember, we're switching directions, less than or equal to negative 2. So we're going to subtract 5 from both sides. So y is greater than or equal to negative 3. Subtract 5 from both sides, and y is less than or equal to negative 7. So if we want to put this on the number line, we put our smallest value first, which is negative 7. Then we have negative 3. So the first says y is greater than or equal to negative 3. So greater than negative 3 is to the right. Because it can equal negative 3, we use a bracket. And now we have, for the second one, y is less than or equal to negative 7. So the values that are less than negative 7 go to the left. And because it can equal negative 7, we use bracket. So writing this in interval notation, we start with the left and work our way to the right. So the point furthest left, it keeps going to negative infinity, and it stops at negative 7. It includes negative 7, so negative 7 gets a bracket. Since we have two intervals, we use the union symbol. The second interval begins at -3 and continues indefinitely to the right, so it goes to infinity. And since -3 is included, we use the bracket. How do we know it's included? We look at our inequality symbol. Anytime it has the or equal to part, we'll be using brackets. Our next example, we have 4 times the absolute value of v minus 9. Minus 2 is greater than 30. So the first thing that we need to do is isolate before we look at our 2. So we're going to add 2. So 4 times the quantity, or excuse me, absolute value of v minus 9 is greater than 32. And then remember, we're dividing by 4. Since we're dividing by a positive, the sign does not change directions. 32 divided by 4 is 8. And here the 4 reduces and leaves us with the absolute value of v minus 9. So now we set up our 2 problems. V minus 9 is greater than 8. And v minus 9, remember, switch, less than -8. So we're going to add 9 to both sides. So v is greater than 17. We're going to add 9 to both sides. And v is less than +1. So again, we come to our number line. Smallest value first, or furthest left. The values that are greater than 17 are to the right. Since it's just greater than and not greater than or equal to, we use parentheses this time. Our other is v is less than 1. The values that are less than 1 are to the left. Since it doesn't include 1, we use parentheses. And again, in interval notation, starting from left to right, the point for this left, since the graph continues indefinitely, is -infinity. It stops at 1. Since 1's not included, we use parentheses. Since we have 2 intervals, we use union. The second interval begins at 17 and continues indefinitely to the right. Since 17 isn't included, again, we use parentheses. The next concepts are polynomial inequalities. So what we're looking at are 2 factors, x plus 7 and x minus 4. We want to know when we multiply them together, when will it give us a value greater than 0? So what we're going to do to solve this, there's different ways to do it, is first identify what our endpoints are. So what I do is I say, let x plus 7 equal 0, and let x minus 4 equal 0. So I have a boundary at -7, and I have a boundary at 4. So when I look at a number line, what I want to do is test certain regions. So I'm going to, again, smallest comes first. So this would be -7 and then 4. So at -7 and 4 is where this particular polynomial, when multiplied together, would give us 0. These are our zeros. But I'm interested in when I multiply the 2 together, when will it give me a value greater than 0 or a positive number? So what I do is I look at the 3 regions. So this is region 1. This would be region 2 between -7 and 4, and region 3 would be those values to the right of 4. So I choose any number I want from each region. Like I may want to choose -8, because -8 falls in that first region. A value between -7 and 4 may be 0. So 0 is going to be my test point for region number 2, and any value greater than 4, maybe 5, will be my test point for region 3. So what I'm going to do is take my test points and plug them in to the given polynomial. So when I choose -8 and I substitute it in for the x and the x plus 7, I would get -8 plus 7 and then -8 minus 4. So -8 plus 7 is -1. -8 minus 4 is -12. And -1 times -12 is +12. This gives me a true statement because +12 is greater than 0. So yes, this worked. So any number that I would choose in this region would be a solution for my polynomial. Next, I'm going to try 0 and plug 0 in for my x's. So I'd have 0 plus 7 and 0 minus 4 and see if that's greater than 0. So 0 plus 7 is 7. 0 minus 4 is minus 4. And 7 times -4 is -28. And -28 is not greater than 0. So the points between -7 and 4 will not work. So no. Then I choose a point to the right of 4. In this case, 5. So when I plug 5 into my inequality for x, I get 5 plus 7 and 5 minus 4. 5 plus 7 is 12. 5 minus 4 is 1. And 12 times 1 is 12. And 12 is greater than 0. So it does work for numbers in this region. So I need to write these in interval notation. So the values to the left of -7 work. So the values from -infinity to -7, and notice I'm using parentheses. Why am I using parentheses? Because the original inequality is just greater than, not greater than or equal to 0. Since I have two intervals, I'm going to use union. The second interval did not work, but the last interval did when I used 5 as my test point. I don't use that in my answer, I use the interval. So the interval began at 4 and continued to infinity. And again, parentheses. So this means any value less than -7 would work when I plug it into my inequality, would give me a true statement, as would any value greater than 4. The next example, I have 3 different zeros or boundary points to use. So remember, I'm choosing the values that make each factor 0. So for the first one of my boundary points would be 8, because 8 minus 8 gives me 0. My next boundary point would be 2, because 2 minus 2 would give me 0. And my last boundary point would be -4, because -4 plus 4 is 0. Next, I'm going to find test points in each of my regions. In this case, I have 4 regions. Values that are less than -4, values that are between -4 and 2, values that are between 2 and 8, and values that are greater than 8. So I could use maybe a -5 as a test point. Between -4 and 2, I could use a 0 as a test point. Between 2 and 8, maybe 3. And greater than 8, 9. So what you're going to do is you're going to plug those test points in to test to see if that particular value would be a solution to the given inequality. In this case, it says less than 0. So what we're looking for are negative answers. So when I plug -5 in, I'd have -5 minus 8 negative 5 minus 2, and negative 5 plus 4. So negative 5 minus 8 is negative 13. Negative 5 minus 2 is negative 7. And negative 5 plus 4 is negative 1. So to make life easier so you don't have to worry about whether or not you get a correct number, we're interested in the sign. So I'm going to take a little bit different approach here. So here when I multiply a negative times a negative, I'd get a positive. If I multiplied a positive times a negative because of this negative 1, my answer would be negative. So a negative is less than 0, so it would work for that value. So again, I'm just looking at signs. If you have an odd number of negatives, your answer is going to be negative. And what are we looking for in this case? A negative, because it says I'm looking for numbers that are less than 0. Okay, you can do it that way, or we can take the actual value, in this case 0, and plug it in. So we'd have 0 minus 8, 0 minus 2, 0 plus 4, and we're interested to see if that's less than 0. So 0 minus 8 is negative 8, 0 minus 2 is negative 2, and 0 plus 4 is 4. When we multiply them together, we get positive 64. And positive 64 is not less than 0, so this does not work. So right now, the values less than 4 worked. The values between negative 4 and 2 do not work. And now I'm going to try a value between 2 and 8, 3. So when I plug in the 3, I'd get 3 minus 8, 3 minus 2, and 3 plus 4 to see if that's less than 0. So 3 minus 8 is negative 5, 3 minus 2 is 1, and 3 plus 4 is 7. So negative 5 times 1 is negative 5 times 7 is negative 35, and negative 35 is less than 0. Therefore, the values between 2 and 8 are solutions. My last would be values greater than 8. So we're using 9 as our test point. So we'd have 9 minus 8, 9 minus 2, and 9 plus 4. So 9 minus 8 is 1, 9 minus 2 is 7, and 9 plus 4 is 13. So when I multiply them all together, I get positive 91, and 91 is not less than 0, so that's not a solution. So my only solutions are those values where you see the yes. So from negative infinity to negative 4, not from negative 4 to 2, because we had no, that didn't work when we used our test point. But we have another interval now from 2 to 8. Why don't I have brackets? Because again, my original problem is less than, not less than or equal to. My next example, same type problem. I want to identify my boundaries or my zeros. X squared plus 9. There's no value of x that I can plug in under the real number system and square it and add 9 to it to get 0. So my zeros would be whatever makes the second factor 0. So we know that 1 minus 1 is 0. And whatever makes x plus 1 0, which is negative 1. So I have two zeros or boundary points at negative 1 and positive 1. So again, I want to see where or which region would produce the numbers that would make this a true statement. So to the left of negative 1, I may use negative 2 as a test point. Now a number between -1 and 1. 0 is always pretty easy to do, so I'll use 0. And any value greater than 1, and again, I like to keep it close and small, so I'll use 2. So I'm going to plug those in. So the first one I do is -2. So I have -2 squared plus 9, 1 minus -2, and then -2 plus 1. I want to see if that's less than 0. So -2 squared. Make sure when you're putting this in your calculator, you do it as you see it. The -2 has to be in parentheses. So -2 squared are 4, and 4 plus 9 is 13. 1 minus a -2, since that's a double negative, becomes 1 plus 2, which is 3. And then -2 plus 1 is -1. So 13 times 3 is 39, times -1 is -39, and -39 is less than 0. So yes, that worked. Next, I want to try 0. So I plug it in for x, and I get 0 squared plus 9, and 1 minus 0, and 0 plus 1, and see if that's less than 0. So 0 squared plus 9 is simply 9. 1 minus 0 is 1, and 0 plus 1 is 1. So 9 times 1 times 1 is 9, and 9 is not less than 0, so that's not a solution. So I try my last region, so I use my test point 2, and I get 2 squared plus 9, then 1 minus 2, and then 2 plus 1. See if that's less than 0. So 2 squared or 4 plus 9 is 13. 1 minus 2 is -1, and 2 plus 1 is 3. So 13 times -1 is -13, times 3 is -39, and -39 is less than 0. So yes, this region would be part of our solution. So yes and yes. So to write my answer, it goes from -infinity to -1, goes to my boundary. Doesn't include because our original inequality is just less than. Since I have 2 intervals, I use union. The next interval begins at 1 and continues to infinity, and again, both inside parentheses. So my last example, we do the same thing even though it's a division problem. We find the zeros or our boundary points. So we have a boundary point at -7 because -7 plus 7 is 0. And we have one at 4 because 4 minus 4 is 0. So now I choose test points. And again, I choose it to the left first. So -8, a number in between -7 and 4. And again, I like to use 0 whenever possible. And a value to the right of 4 on the number line. And that could be 5. So now I plug them in. So I start with -8. So -8 plus 7 and -8 minus 4 has to be greater than or equal to 0, which means it has to be positive or 0. So -8 plus 7 is -1. -8 minus 4 is -12. A negative over a negative is positive. So 1/12 has to be greater than or equal to 0, and it is. So yes, it worked for the values less than -7. Now I'm going to use 0. So I have 0 plus 7 over 0 minus 4 has to be greater than or equal to 0. 0 plus 7 is 7. and 0 minus 4 is negative 4. A positive over a negative is a negative, and it would not be greater than or equal to 0. So this does not work. The last value I'm going to use is the test point 5. So I'd have 5 plus 7 over 5 minus 4. 5 plus 7 is 12. 5 minus 4 is 1. And 12 over 1 is 12. And 12 is greater than or equal to. It only has to be 1. It doesn't have to be both. So since 12 is greater than 0, yes, that region works. Now here's the only twist as far as your answer is concerned. Notice the original says greater than or equal to. That means our answer can be 0. And remember, these values, our boundary points, are potential zeros. So now I know that the values less than negative 7 worked, because when I plugged in negative 8, it gave me a value greater than 0. So from negative infinity to negative 7, I'm going to work on the grouping symbols in a minute. Since we have a second interval, I put union, and that second interval began at 4, and it continues indefinitely to infinity. So we know always infinities get the parentheses. Now again, looking back at our original problem, since it's greater than or equal to, our answer can be 0. So we know if we plug negative 7 into this, negative 7 plus 7 makes my numerator 0, which is okay. It's allowed. So I'm going to use a bracket. Now, even though 4 was our boundary point, 4 cannot be included, because if 4 were included, it would make my denominator 0, which is undefined. So for the 4, you have to use parentheses. So even though in your boundary points, if this were a polynomial and not a fraction, both would have brackets. But you need to pay attention. If either or any part of your boundaries would make your denominator 0, it will always have a parenthesis around it.